You have been hearing the word algebra since your early school days. In middle school, you took an algebra course. In high school, you studied advanced algebra. Often, you might say, I'm doing algebra now. However, if someone were to ask you to define what algebra actually is, you might find yourself at a loss for words. Although you've been taught how to do algebra, it's quite strange that you were never really taught what algebra is. In this first video, I will explain what the algebra of numbers means. In the follow-up video, I will make the concept even more precise by introducing the idea of a general algebra. As you will soon realize, it's a term that carries a lot of depth and importance. Let's start with an example. Suppose you're given the expressions 2a and b minus 3a, and you are asked to add them. You might quickly respond with b minus a. You're so accustomed to performing algebraic calculations that you may not even notice the multiple steps involved in obtaining the answer. So, let's review those steps. The steps you use to derive the answers in any calculation are the mathematical laws which define an algebra. In other words, the algebra of numbers in the set of real numbers is the structure that we have created by specifying particular relations among the numbers. Let's take things from the beginning and slowly build our way to the algebra of numbers. The set is the most basic concept in math. It is a collection of objects usually having a property, but there is no other relation among themselves. For example, think of the set of all people on Earth. As a set, it only contains all human individuals. However, we cannot say anything else for these individuals. Once we introduce relations among humans, such as husband and wife, employer and employee, etc., then the set becomes more interesting, and we can start exploring consequences of the relations. The same is true for mathematical sets. They become more interesting if we define relations among their members. More precisely, the members of a set in mathematics are called elements of the set, and the relations among the elements of the set are called binary relations. Among all possible binary relations, we are interested in those that map all possible pairs of the set to an element of the set. These are functions from the Cartesian product S cross S to S, and we call them binary operations. Hence, in the set of real numbers, we define two operations known as addition and multiplication. These operations take two elements A and B and map them to another element, S and M respectively. The rules how to create the images S and M, which are called sum and product respectively, are given through a set of axioms which are not of importance here. The result is the standard operations of addition and multiplication as you know them. Also, as you know very well, instead of using the standard notation of functions, S and M are simply indicated by a plus and a dot between the two elements A and B. Let's look at the addition first. It has the following four properties. 1. Commutativity. That is, a number can be left or right added to another number to obtain the same sum. 2. Associativity. That is, the order we add three numbers does not change the result. 3. Existence of a zero. That is, there exists an element, known as the zero, such that when it is added to a number, the sum is the number itself. 4. Existence of opposites. That is, for each real number A, there exists another real number, known as the opposite of A, such that their sum is the zero element. When the set of real numbers is endowed with the addition of numbers, a structure is established which exhibits the previous properties. Such a structure is called an abelian group. The adjective abelian stresses the commutativity of addition. Without this property, the structure is called a group. Some mathematicians use the adjective commutative instead of abelian. Similarly, when the set of real numbers is endowed with the multiplication of numbers, a structure is established which is also an abelian group. In particular, multiplication has the following properties. 1. Commutativity. That is, a number can be left or right multiplied to another number to obtain the same product. 2. Associativity. That is, the order we multiply three numbers does not change the result. 3. Existence of a unit. That is, there exists an element, known as the unit, such that when it is multiplied to a number, the product is the number itself. 4. Existence of inverses. That is, for each non-zero real number a, there exists another real number, known as the inverse of a, such that their product is the unit element. It is important to note that it is the set R** which becomes an abelian group with multiplication, not R, since the zero element has no inverse. So, the set of real numbers with the addition and multiplication has two abelian group structures. These structures are unrelated unless we introduce a way to link them. The link is provided by the distributive property. This way we have established a very rich structure in the set of real numbers. This structure is now called a field. Any calculation you have ever done in your math classes goes back to the properties I just enumerated in this video. Let's see an example. Consider the well-known identity. The steps proving the identity are as follows. The last expression can be written without the parenthesis since the expression is unambiguous due to the associativity of addition. Thus, we have arrived at the result sought. The structure of a field can be created inside any set F if two operations star and circle are defined such that each of them creates an abelian group and linked by the distributive property. The star operation can be thought as the additive operation of the elements and the circle operation as the multiplicative operation of the elements. And like in the real numbers, the zero element of the star operation cannot have an inverse. Any result that was proven for the real numbers is also true for the elements of F, since the relations among its elements are identical. As an example, let F be the set of all numbers of the form q plus p times square root of 2, with p and q any rational numbers. Then, given two numbers alpha and beta in F, we define their sum and product as follows. Then, as a routine exercise to check that F endowed with the addition is an abelian group. Similarly, F asterisk endowed with the multiplication is an abelian group. The distributive property also holds. Hence, F is a field. Many important results in modern mathematics are based on fields thus constructed and other algebraic structures, which will be explained in the follow-up video. If the set of real numbers endowed with the operations of addition and multiplication is a field, what and where is the structure of the algebra? An algebra is an even more complicated structure, and it needs two sets and 5 operations. Unfortunately for the real numbers, the second set is a copy of the set of real numbers with the same addition and multiplication. The two sets do create an algebra, but it is impossible to differentiate this structure from just the field structure. The simplicity of the real numbers hides the complexity of the algebra. To uncover it, we must necessarily define it in another set and then return to the real numbers to fully understand how it is hidden. The simplest algebra is the one we can build with R cubed, whose elements are the three-dimensional vectors. In this set, we have an addition which gives R cubed an abelian group structure. The elements of R cubed, the vectors, are multiplied by numbers which belong in the field of real numbers. As we will better explain in the follow-up video, The structure we have built up to this point is a vector space. To create an algebra, we add a second operation in R-cubed, that of the cross product of two vectors. With this operation added, we have now an algebra. However, because the cross product is not associative, we call this algebra non-associative algebra. Perhaps, using this superficial explanation of an algebra, you can see how the algebra of the real numbers is hidden within the field structure. In a follow-up video, I will be more precise about the definition of a vector space, algebra, and other related structures. At the moment, you should just retain that the field of real numbers is a structure made of two abelian groups, determined by the addition and multiplication, which are linked by the distributive property. You have now made your first steps in the exciting terrain of algebra. This area is full of exquisite ideas and results. As you continue your walk and explore it, expect to be amazed. I hope you liked this presentation. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.